Hey guys, hope you are doing well. Today, we will have some applications of the mole. We're still in the chemical calculations in chapter 5. We already studied what is the mole and the conversion of mole into mass and the conversion of mole into a number, which is Avogadro's number. And now we need to use the information that we have about the mole in some applications. First application is the limiting reactant and the reactant in excess. The limiting reactant and the reactant in excess. If you have a substance A that reacts with a substance B to give C. So these are the reactants and this is the product. Usually in the chemical reaction, we know the amount needed of each reactant to give a certain amount of the product. And we know that from the number of moles used from each reactant. Here we have 1 mole of A needs 1 mole of B to give a product C. What if we put one of them in excess? In this example, our normal chemical equation, this is exemplified. We need only 1 mole from A to react with 1 mole with B. What if we add 1.5 mole of A? And we add it to 1 mole of B. What do you expect to happen? Exactly. Only 1 mole of A will react with 1 mole of B. Only 1 mole of A will react with 1 mole of B for the reaction to proceed and give C. But the 0.5 mole of A will be excess, will be extra. And what will happen for this half mole? What will happen is that this half mole will remain unreacted in the reaction medium. In that case, we call A, because it has extra amounts than needed, a reactant in excess. A reactant in excess is a reactant that exists in the reaction in excess in an extra amount, and this extra amount will not totally consumed during the reaction. Some of it will be consumed and the remaining amount will remain unreacted in the reaction medium. What about B? B will be totally consumed because this is the real amount that we need. So 1 mole of A, only 1 mole of A will react with this 1 mole of B to give C. So B will totally consumed. So B in that case is called limiting reactant. So it is the reactant that already consumed totally during the reaction. How can we know that we have excess or limiting reactant? We have to compare the amount that we have, that we are given in the problem, to compare it with the standard chemical equation of these reactants. And then when we compare them, we will know if these reactants all are enough to be totally consumed during the reaction, or one of them will be totally consumed and the other will still have excess value that will remain in the reaction. And to know that, we have to recall our information about the mole and the calculation using the mole. Let's know the definitions first. The limiting reactant is the reactant that doesn't exist in excess, will not have an excess amount after the reaction takes place, which is reactant that is completely consumed during the chemical reaction. And upon the reaction, it will produce the lowest number of moles of the product. We have one problem to solve it, to get more idea about the limiting reactant and the reactant that exists in excess. We have cobalt carbonate. This is 1 mole of cobalt carbonate reacts with 2 moles of hydrochloric acid to give 1 mole of cobalt chloride and 1 mole of HGO, in addition to 1 mole of carbon dioxide gas. This is the standard chemical equation. This is the standard chemical equation. But in our example, the chemist used 6 grams of cobalt carbonate and added to it 0.08 mole of hydrogen chloride or hydrochloric acid. From the standard equation, to know which is the limiting reactant or which is the reactant that exists with in excess, we need to compare the amount that is actually added to the standard amount that is supposed to be used. We know that the standard amount that is supposed to be used is an amount equivalent to 1 mole of cobalt carbonate and 2 moles of hydrochloric acid. So the hydrochloric acid is double the number of moles of hydrochloric acid is double the number of moles of cobalt carbonate. So if the chemist added 0.08 moles of hydrochloric acid, we expect, depending on the standard equation, that these 0.08 moles of HCl will need only 0.04, half the number of mole, not the amount, half the number of mole of cobalt carbonate. This is the standard. So if every 1 mole of cobalt carbonate needs 2 moles of hydrochloric acid, so if we put 0.08 mole of hydrochloric acid, we will need 0.04 mole of carbon carbonate, because the standard equation tells us this information, that the number of moles of HCl is double the number of moles of cobalt carbonate. So what exactly happened? What exactly happened is that only 6 grams of cobalt carbonate is added. So we need to know whether these 6 grams are equivalent to the supposed number of moles that is equivalent to this amount of HCl or not. How can we do that? To do that, we need to recall our information from the mole calculation. We know that the mole and the molar mass, how to convert the mole and into molar mass. How to do that? We need to convert this 6 gram into moles, to know how exactly, how many number of moles of cobalt chloride is exactly added in this reaction. So we'll depend on our triangle. add here the number of moles, and here's the molar mass, and at the top is the mass, the actual mass of the substance. And usually whatever in the top is divided by whatever in the bottom, and the two beside each other are multiplied. So if we need the mass, we will multiply the mole by molar mass. If we need the number of moles, we will divide the mass by the molar mass. Okay, so we'll need to convert the 6 gram of cobalt chloride into number of moles. So the number of moles of the actual number of moles of cobalt carbonate equal the mass, which is 6 grams, divided by the molar mass. So what is the molar mass of cobalt carbonate? We need to recall how we calculate the molar mass. We calculate the molar mass by adding the masses of the molar masses of the elements in that substance together. So to do that, we are given the molar masses of each atom that we have here. So the molar mass of cobalt carbonate, 1 cobalt is 59 plus 1 carbon. The molar mass of carbon is 12 from here, plus 3 oxygen. So 3 times 16, 3 times 16 is 48. If you have a problem in calculating the molar mass, you will need to go back to watch the video of the molar mass, the mole, converting the mole into mass and converting the mass into moles. This will equal to 6 by 119, and this equals to 0.05. And from our calculations, this 6 grams is equivalent to 0.05 moles. But we need only 0.04 moles. So the amount added, which is the 6 grams, is equivalent to a number of moles, which is more than needed. We need only 0.04, but the chemist added 0.05, an amount needed. So only 0.04 will react with the 0.08 mole of hydrogen chloride, and the remaining 0.01 mole will remain unreacted. So here the limiting reactant is the hydrochloric acid, and the reactant in excess is the cobalt carbonate. Why? Because the amount of cobalt carbonate is more than the actual amount needed. How do we know that? We compare the amount added with the standard balanced equation. You have to get the balanced equation to make sure that your equation is balanced. And then after that, we have to compare the amount that's supposed to be added with the amount that actually added. The tricky point, if you get an amount in grams and the other in moles, we have to convert either the mole into grams and the grams into moles. And it is easier in that case here to convert the grams into moles, because from here we know how many moles are added, and these moles require how many moles of the other substance. This is the answer. Each 1 mole of cobalt carbonate needs 2 moles of hydrochloric acid. So how many moles of cobalt carbonate will need? 0.08 mole of hydrochloric acid. Then it is calculated in details. The molar mass of the cobalt carbonate is 119, depending on this table. We added the molar masses of each element in the compound. And then we, after calculation, that we found that these 6 grams are equivalent to 0.05 cobalt carbonate. And it means that cobalt carbonate exists in excess. Here we need to know which is the limiting reactant and which is the reactant that exists in excess. We have magnesium reacts with oxygen to give magnesium oxide. And this is a balanced equation, 2 magnesium, and they come out as 2 magnesium and 2 oxygen, and we have here 2 oxygen. So each 2 moles of magnesium needs 1 mole of oxygen. Each 2 moles of magnesium needs 2 mole of oxygen. What is actually happened that the chemist added 32 grams of oxygen to 12 grams of magnesium. The situation here is different because we are comparing grams to grams. We will need first to convert the number of moles in the standard equation into grams, or we need to convert these grams into number of moles, whatever is easier for you. So if we convert these 2 magnesium into grams, we will compare it with this 32 with this 12 grams of magnesium, or the opposite. Here in the answer, we used the gram conversion. We have an information that every 2 moles of magnesium needs 1 mole of oxygen. Okay, so when we calculate the 2 moles of magnesium, it equals to 48 because the molar mass of 1 magnesium is 24. 24 by 2 because they are 2 moles. So we have 48 grams of magnesium. They need 32 grams of oxygen. How can we know that? Because 1 mole of oxygen, O2, equals to 32 grams. 2 times 16. From the standard equation, we get this information. We converted the number of moles into grams to know how many grams of magnesium needs how many grams of oxygen. So in reality, in the standard equation, every 48 grams of magnesium will need 32 grams of oxygen. But what we do is that we added 32 grams of oxygen to only 12 grams of magnesium. The amount of magnesium that is added actually to the reaction is a way less than the amount that actually needed. The amount that actually needed for this 32 grams is 48. So we add quarter the amount, which means that the 12 grams will totally react and there will be excess of O2 that want to be reacted and remain in the reaction medium. As the magnesium is less than the standard amount, the magnesium is the limiting reactant, while O2 will exist in excess. Another example, same reaction, but with different amount. Here, 15 grams of oxygen was added to 20 grams of magnesium. From the previous calculation, because this is the same equation, we know that each 48 grams of magnesium needs 32 grams of oxygen. And how we know that? By converting the number of moles into more molar masses. So this is equivalent to 2 moles of magnesium, and this is equivalent to 1 mole of oxygen. And this is the standard. This information we predicted from the standard equation. And this is the actual amount that is added. The chemist added 20 grams of magnesium. So these 20 grams will need how many grams of oxygen? We cross it. So we'll multiply 32 by 20 divided by 48, and we will get this number. Every 20 gram of magnesium needs 13.33 grams of oxygen. But the chemist added 15 grams of oxygen. 15 is more than 13, which means that more amount of oxygen that needed was used. So oxygen is in excess while magnesium is the limiting reaction. All the amount of magnesium will react with only 13.3 grams of oxygen, and the remaining of the 15 will remain unreacted of oxygen. So oxygen is in excess while magnesium is the limiting reactant. Another example, the same equation, magnesium plus oxygen gives magnesium oxide. But here 60 grams are added to of oxygen to 52 grams of magnesium chloride. Each 2 moles of magnesium needs 1 mole of oxygen. In this problem, we will use the opposite way of conversion. I mentioned that we can convert if we have something in grams and the other in moles. We can convert the grams into moles or the moles into grams to have a standard comparison between them. In the previous two examples, we converted the moles into grams. Here we will convert the grams into moles. Whatever you will use, it's up to you. Whatever is more comfortable for you, use it. Feel free to use it. Here we will convert the grams into moles. From the standard equation, we know that each 2 grams of magnesium needs only each 2 moles of magnesium needs only 1 mole of oxygen. This is given information. In our example, we added 60 grams of O2 to 52 grams of magnesium. So we need to know how many moles in this 60 grams and how many moles in this 52. And we are given the molar masses of each atom. We can easily convert the mass into number of moles by the equations that we have, or we can just draw the triangle that we used to draw to remember how to calculate it. Here we have the mole. Here we have the molar mass. Here we have the mass. We already have the mass in our example, which is the 60 grams. And the molar mass is calculated from the molar masses. And then we will need to calculate the mole. So the mole will equal to the mass divided by the molar mass. So number of moles will equal mass divided by molar mass. The molar mass of oxygen is 32. Oxygen is O2. And the H1O has a molar mass of 16. 16 times 2 is 32. And the mass that we have is 60. And the answer is 1.88 moles. This 60 grams equivalent to 1.88 moles. So what is the number of moles of magnesium? Same way, we'll use the same way. Mass over the molar mass. The mass that we have is the 25 grams, 52 grams. And the molar mass of magnesium, Mg, is 24. So 52 over 24 will equal to 2.17. For each 1 mole of oxygen, we need 2 moles of magnesium. So if we have 1.88 of O2, we will need double this number for magnesium because each 1 mole needs 2 moles. So each 1.88 will need 1.88 times 2 moles of magnesium, which is 3.76. The needed amount is 3.76 of magnesium, but the added amount is only 2.17. The added amount of magnesium is less than the needed amount. So these 2.17 moles will totally react with the moles of oxygen, with the required moles of oxygen, and we will have some more oxygen remain in the reaction. As the magnesium is less than the amount needed, magnesium is the limiting reactant while oxygen will exist in excess. Here we go. Another example, magnesium, same equation. We have other example. Now we have 1.5 mole of magnesium react with 2.1 mole of oxygen, and we know that each 2 moles of magnesium needs 1 mole of oxygen. Therefore, each 1.5 mole of magnesium, the number of moles of magnesium is double the number of moles of oxygen. Remember, 1.5 is the double of the number of moles of it. So 1.5 of magnesium will need 0.75 mole of oxygen. This is the standard requirement. But what is actually added is 2.1 mole of oxygen if we compare the actual amount added with the required amount. The amount added is higher than the required amount. So here in that case, oxygen is added in excess, while magnesium is the limiting reactant. I hope when you see a problem, try to solve it yourself without looking at the answer and see what you will get. It's your own decision to convert moles into grams or grams into moles if you have both of them in your problem. So if you have moles and grams, but if both are moles, you don't need to convert the moles into grams. You will compare number of moles. I put many examples so you have more chance to answer. Another example, nitrogen, 1 mole of nitrogen reacts with 3 moles of hydrogen to give 2 moles of ammonia. This is the standard chemical equation of the reaction between nitrogen and the hydrogen. What is actually added is 0.4 moles of nitrogen and 3 grams of hydrogen. Remember, from the standard equation, we know that the number of moles of hydrogen needed is triple the number of moles of nitrogen needed. So every 1 mole of nitrogen needs 3 moles of hydrogen. If we added 0.4 mole of nitrogen, how many hydrogen we need? We have to multiply, triple the amount. We have to multiply this amount by 3. Which is 1.2. We need to know how many grams in this mole because we are given the amount of hydrogen into grams. To know how many grams is needed, how many grams exist in this number of moles, we divide it by the molar mass. Which is 1. The molar mass of the hydrogen is 1. It's the same 1.2 grams of hydrogen. And now we can compare them. From our calculation, we get that H2 exists in excess, while N2 is the limiting reactant. We'll need you to answer this problem to calculate whatever is added of magnesium and oxygen, and then to find out which of them is the limiting reactant and which of them is the reactant that is in excess. Just have a screenshot and try to answer it and write down the comments down below. You don't need to write the full answer. You make the full answer in your paper and write in the comments which is the limiting reactant and which is the reactant in excess. Try to answer this too, but take care that here we have moles and grams. So you can convert whatever to whatever as you feel comfortable. But at the end, we need to know what is the limiting reactant and what is the reactant in excess. This equation 2. And that's all for today. I hope the idea of limiting reactant and reactant in excess is clear now. We had many examples, and I hope you will solve the other examples yourself. Don't neglect it because the calculations depend as the math, consider it as math. So you will not be good at math without answering, without solving the problems. The same, you want to be good at chemical calculations without solving more and more problems. Thank you guys for watching and see you in the next video. If you have any question, write it down in the comments down below. Thank you and bye-bye.